Welcome to this walkthrough of LeetCode problem number 494, target sum. In this problem, we explore how to assign plus and dash signs to a given set of numbers to achieve a target sum. This challenge tests our understanding of dynamic programming and recursion. Let's dive in and examine different approaches to solve this problem. In this problem, you are given an integer array called nums and an integer target. The task is to form mathematical expressions using the integers and nums by adding either a plus sign, represented by plus, or a minus sign, represented by dash, in front of each number. Once you've assigned these signs, the resulting expression should evaluate to the value of target. The objective is to determine how many distinct ways you can assign these signs to achieve the given target value. Now, the input format includes the array nums, which contains non-negative integers, and the integer target. The output is a single integer, representing the total number of valid expressions that satisfy the given condition. This is a problem that combines combinatorics with arithmetic operations, and understanding the constraints will help us tackle it more effectively. To understand the problem better, let's look at the first example. Suppose nums is 1, 1, 1, 1, 1, and target is 3. The task is to figure out how many different ways we can assign plus and minus signs to the numbers in nums to make the sum equal to 3. The output in this case is 5, because there are exactly 5 distinct expressions that evaluate to 3. These expressions are plus 1 plus 1 plus 1 plus 1 dash 1, plus 1 plus 1 plus 1 minus 1 plus 1, plus 1 plus 1 minus 1 plus 1 plus 1, plus 1 minus 1 plus 1 plus 1 plus 1, and dash 1 plus 1 plus 1 plus 1 plus 1. Each of these combinations uses the numbers in the array exactly once, with either a plus or minus sign, and the sum matches the target. In the next example, nums is 1, and target is 1. Here, the task is simpler because there's only one number in the array. The only valid way to assign a sign is by using a plus sign, resulting in the expression plus 1, which evaluates to 1. Therefore, the output is 1. This example highlights that when the array contains just one element, the solution is straightforward, as there are only two possible sums, adding the number or subtracting it. This simplicity makes it a good base case for understanding the problem. Another example is when nums is 1, 2, 3, 4, 5, and target is 10. In this case, the output is 1, because there is only one valid expression that evaluates to 10. That expression is plus 1 plus 2 plus 3 plus 4 dash 5. This example demonstrates how the problem scales as the array becomes larger and how the combinations of signs can become more complex. The challenge lies in identifying all valid expressions efficiently, especially as the length of nums increases. To solve this problem effectively, we need to consider the constraints. The length of nums is between 1 and 20, which means we might need to evaluate up to 2*20 combinations in the worst case. Each number in nums is non-negative, and their sum ranges from 0 to 1000. The target value is bounded between dash 1000 and 1000. Edge cases include situations where the array contains only one number, where the target is outside the possible sum range, or where all numbers in nums are zeros. For example, if all elements are 0, the only way to achieve target equals 0 is by assigning all signs as either plus or all as dash. For any target not equal to 0, the result would be 0 ways. These constraints and edge cases are critical to designing an efficient and robust solution. To tackle the target sum problem, we can start with the brute force approach, which uses recursive exploration. The idea here is simple. For each number in the given array, we decide whether to add or subtract it, and then keep track of the resulting sum. This process continues recursively, branching into two possibilities at every step, adding the current number or subtracting it. If we reach the end of the array and find that the current sum matches the target, we count it as a valid solution. While this approach is intuitive, it has significant limitations. The time complexity grows exponentially, 2 to the power of n, because we are exploring all possible combinations of signs. Additionally, the recursion stack requires n space. For larger inputs, this method becomes inefficient and impractical due to the sheer number of combinations that need to be explored. To improve efficiency, we can use an optimized approach based on dynamic programming by transforming the problem into a subset sum problem. Here's the intuition: instead of explicitly adding or subtracting signs, we can think of splitting the array into two groups, one group with a positive sign and the other with a negative sign. Let's call the sum of the positive group P and the sum of the negative group N. The total sum of all elements in the array, S, satisfies the equation P plus N equals S. Additionally, since we want the difference between P and N to equal the target, we know P, N equals target. By combining these equations, we derive that P equals S plus target, /2. This means the problem can be reduced to finding subsets of the array whose sum equals S plus target, /2. Dynamic programming is well suited for solving this kind of subset sum problem efficiently. The algorithm for this DP-based approach begins by first ensuring that the problem is valid to solve. If the sum of S and the target is odd, or if the target is out of range, say, larger than the total sum S, we immediately return 0 because no solution is possible. Next, we define a DP array, DP, where DP, J, represents the number of ways to achieve a sum J using the elements of the array. We initialize DP, 0, to 1, as there is exactly one way to achieve a sum of 0, which is by not including any numbers. Then, we iterate over each number in the array and update the DP array by adding the number of ways to form the current sum using that number. At the end of the process, the answer to our problem is stored in DP, S plus target, /2. This approach is significantly faster than brute force, as it avoids redundant calculations by reusing intermediate results. The time complexity is O, n asterisk sum, nums, where n is the length of the array, and the space complexity is O, sum, nums, due to the DP array. There are alternative approaches to solving this problem that are worth mentioning. For example, memoized recursion combines the brute force approach with a memo table to avoid redundant calculations. While it improves the time complexity to O, n asterisk sum, nums, the space complexity increases because we need to store results for all combinations in memory. Another approach is bit masking, where we represent the signs as binary states and evaluate all possible combinations. However, this method is conceptually similar to brute force and not practical due to its high complexity. Ultimately, the dynamic programming approach stands out as the most efficient and scalable solution. The key realization here is that the problem can be reformulated as a subset sum problem, which is well suited for dynamic programming. This transformation allows us to solve the problem efficiently while handling larger inputs. The relationship between the total sum S and the target gives us the mathematical insight we need to avoid the inefficiencies of brute force. When using the dynamic programming approach, it is important to acknowledge the trade-offs. While this method is faster and avoids redundant calculations, it requires careful handling of edge cases, such as when the sum of S and the target is odd or when the target is outside the achievable range. Memoized recursion, though another viable option, is less space efficient because it requires additional memory for storing results. In conclusion, the dynamic programming approach strikes the best balance between time and space complexity, making it the optimal choice for solving the target sum problem. By leveraging the subset sum transformation and using the DP array effectively, we can handle larger inputs and solve the problem efficiently. In this problem, we are given an array of numbers, and the task is to assign either a plus or a minus sign to each number, exploring all possible combinations of these assignments. The goal is to calculate the resulting sums from these combinations. To solve this, we use a brute force recursive approach. The algorithm begins with the input array nums and a helper function that tracks our progress through the array using an index I and the current accumulated sum, current_sum. The base case occurs when we have processed all elements in the array, at which point we record the current_sum and exit the recursion. For each number in the array, there are two possible paths. We can either add the number to the current sum or subtract it. This branching process creates a decision tree that systematically explores all possible combinations of signs for the numbers. In the recursive step, for every number at the current index, we calculate two new potential sums, one where the number is added and another where the number is subtracted. These two paths are explored recursively by incrementing the index I and updating the current_sum accordingly. Once all recursive calls are completed, we collect the unique sums that were generated and return the results list. This approach leverages recursion to examine every possible configuration of plus and minus signs, ensuring that no combination is missed. However, it's important to note that this method has exponential complexity, as there are 2n combinations for an array of size n. The base case ensures that recursion terminates correctly, and we only record sums when all numbers have been processed. Edge cases, such as an empty array or an array with a single element, are also handled. For example, an empty array produces a single sum of 0, while an array with one number produces two sums, the number itself and its negation. To implement this algorithm, we use two key data structures, the recursive stack and the results list. The recursive stack is used to track intermediate states, such as the current index and the accumulated sum, while the results list stores the final sums generated from all combinations. This allows us to efficiently collect the distinct outcomes of the recursive process. Here's an example implementation in Python. We define a function calculate_sums that takes the array nums as input. Inside it, a recursive helper function DFS is defined to handle the branching logic. The base case checks if we've processed all elements of the array, and if so, appends the current_sum to the results list. The recursive cases explore both possibilities, adding the current number to the sum and subtracting it. We initialize the recursion with an index of 0 and a starting sum of 0, and after all recursive calls are complete, we return the results list containing the generated sums. Let's analyze the complexity of this approach. The time complexity is 2 to the power of n, since each number in the input array leads to two recursive branches. This exponential growth comes from the need to explore all possible combinations of plus and minus signs for the numbers. The space complexity is n, as the maximum depth of the recursion is equal to the size of the input array. Now, let's walk through an example. Suppose the input array is 1, 2. We start with DFS 0, 0. At the first level, we explore adding 1 to the sum, which gives us DFS 1, 1, and subtracting 1, which gives DFS 1, minus 1. From there, for each branch, we consider adding or subtracting 2. For instance, from DFS 1, 1, we calculate DFS 2, 3, and DFS 2, minus 1, adding 3 and dash 1 to the results. Similarly, from DFS 1, minus 1, we calculate DFS 2, 1, and DFS 2, minus 3, adding 1 and dash 3 to the results. The final results list is 3, minus 1, 1, minus 3. To optimize this approach, we can implement memoization to store previously computed results for the same state, avoiding redundant calculations. For larger input arrays, the exponential nature of the brute force approach becomes computationally expensive. To make the algorithm more efficient, we can use dynamic programming to reduce redundant calculations and systematically build up solutions for smaller subproblems. By leveraging dynamic programming, we can avoid recalculating intermediate results and significantly improve performance for larger datasets. This solution uses a recursive backtracking approach with memoization to solve the target sum problem efficiently. Here's how it works, line by line. 1. Memoization dictionary. The memo dictionary is initialized to store the results of subproblems. Each key is a tuple, index, current_sum, and the value is the number of ways to achieve the target from that state. 2. Recursive function backtrack. This function takes two parameters, index, the current position in the nums list, and current_sum, the sum accumulated so far. It explores all possible combinations of adding or subtracting the current number. 3. Base case. When index equals the length of nums, we've processed all numbers. If current_sum matches the target, return 1, indicating a valid combination. Otherwise, return 0. For memoization check, before recalculating, the function checks if the result for the current index, current_sum, is already stored in memo. If so, it immediately returns the cached result, avoiding redundant calculations. 5. Recursive calls. The function computes the results for both adding and subtracting the current number. It recursively calls itself with index plus 1 and updates current_sum accordingly. 6. Store results in memo. After calculating the total number of ways, by summing the results of add and subtract, the result is stored in memo for future reference. This ensures that overlapping subproblems are solved only once, improving efficiency. 7. Driver function. The recursion is initiated with index equals 0 and current_sum equals 0. The final result is returned, representing the total number of ways to achieve the target sum. This approach has a time complexity of approximately n*sum, where n is the length of nums, and sum is the range of possible sums. By using memoization, we significantly reduce the exponential growth of recursive calls, making the solution efficient for larger inputs. Here, we start by importing the necessary Java utilities, and then we define our solution class. The main method we are focusing on is find_target_sumWays, where we aim to determine the number of ways to assign plus and dash signs to elements in the nums array so that their sum equals the given target. To optimize our solution, we use a memoization map, which stores the results of subproblems to avoid redundant calculations. This map uses a string key formed by combining the current index and the ongoing sum, ensuring we uniquely identify each state. The method then calls a helper function, backtrack, which will recursively evaluate all possible combinations of adding and subtracting numbers. In the backtrack function, we first handle the base case. If the index equals the length of the array, we check if the current sum equals the target. If it does, we return 1, indicating one valid way, otherwise, we return 0. Before proceeding further, we check if the memoization map already contains the result for the current state. If it does, we directly return the pre-computed value, saving computational effort. Now, if the result is not already memoized, we proceed to explore the two possible choices for the current number, adding it to the current sum or subtracting it. We recursively call backtrack for both cases, first by incrementing the index and adding the current number to the ongoing sum, and then by incrementing the index and subtracting the number from the sum. These calls return the number of valid ways for each respective branch. The total number of ways for the current state is the sum of these two results. We then store this total in the memoization map using the unique key for the current state, ensuring we can reuse it later if needed. Finally, we return the memoized result, which represents the total number of ways to achieve the target sum from this state. This recursive approach, combined with memoization, ensures that the solution is both correct and efficient. In this example, we have nums equals 1, 1, 1, 1, 1, and a target of 3. The task is to assign either plus or dash to each number in nums so that their sum equals the target. To solve this, we start with an initial recursive call where the index is 0 and the current sum is 0. At each step, we explore two options, adding the current number to the sum or subtracting it. For instance, at index 0 with a current sum of 0, we can either add nums 0, which is 1, to move to index 1 with a sum of 1, or subtract nums 0, to move to index 1 with a sum of dash 1. Additionally, we use memoization to store results for each combination of index and current sum. This avoids redundant computations by reusing previously calculated results. Finally, when we reach the base case where the index equals the length of nums, we check if the current sum matches the target. If it does, we count this as one valid way, otherwise, we return 0 for this path. At the next step, let's consider index 1 with a current sum of 1. Again, we have two options, adding nums 1, which is 1, to move to index 2 with a sum of 2, or subtracting nums 1, to move to index 2 with a sum of 0. This process continues recursively for all indices, exploring every possible combination of plus and dash assignments. Throughout the recursion, memoization ensures that each subproblem is computed only once. For example, if we encounter an index and current sum that has already been calculated, we directly reuse the stored result without recomputing. Once all paths are explored, we find that there are 5 distinct ways to assign signs to the numbers in nums such that their sum equals the target. In the second example, we are given nums equals 1, 2, 3, and a target of 1. The goal remains the same, assign plus or dash signs to the numbers in nums so that their sum equals the target. Starting with an initial recursive call at index 0 and a current sum of 0, we explore two options, adding or subtracting nums 0, which is 1. This leads to index 1 with either a sum of 1 or dash 1. As we continue, memoization helps us avoid redundant calculations by storing results for each combination of index and current sum. At index 1 with a sum of 1, for instance, we can add nums 1, which is 2, to move to index 2 with a sum of 3, or subtract nums 1, to move to index 2 with a sum of dash 1. Similarly, at index 2, we explore all options for the final number, nums 2, which is 3. After exploring all possible paths and leveraging memoization to optimize the process, we determine that there are two distinct ways to achieve the target sum of 1 in this example. Next, we move on to a third example where nums equals 2, 1, 3, and the target is 4. As always, we begin with an initial recursive call where the index is 0 and the current sum is 0. At index 0, we can add nums, 0, which is 2, to move to index 1 with a sum of 2, or subtract nums, 0, to move to index 1 with a sum of -2. As we progress through the indices, memoization continues to play a critical role in preventing redundant computations by storing and reusing results for previously encountered combinations of index and current sum. At the base case where the index equals the length of nums, we check whether the current sum matches the target and count the path if it does. Now let's examine the intermediate steps of the third example. At index 1 with a current sum of 2, we can add nums, 1, which is 1, to move to index 2 with a sum of 3, or subtract nums, 1, to move to index 2 with a sum of 1. At index 2, we explore both options for the final number, nums, 2, which is 3. After evaluating all possible paths, we find that there is only one way to assign signs to the numbers in nums such that their sum equals the target of 4. To summarize the key points, we use recursive backtracking to explore all possible assignments of plus and dash signs, memoization to avoid redundant computations, and a base case where we check if the current sum matches the target. The solution is efficient, with a time complexity of n*sum, nums, where n is the length of the array. By balancing recursion with memoization, we achieve an optimal solution to this problem. Here, we analyze the time complexity of our solution by breaking it down into the number of subproblems and the work required for each subproblem. First, the number of subproblems is determined by the recursive function backtrack, which is called for every combination of index and current_sum. The index iterates over the length of the array nums, denoted as n, while current_sum can take values ranging from sum, nums, to plus sum, nums. This range is proportional to the sum of all elements in nums, which we call s. Consequently, there are at most 2 s plus 1 unique values for current_sum, leading to a total of n*s subproblems. Next, for each subproblem, the work done involves 2 recursive calls and storing results in the memoization table, which occurs in constant time, or O1. When we combine these, the total time complexity becomes n*s, where n is the length of the input array and s is the sum of all elements in nums. Now, let's shift our focus to the space complexity, which has 2 major components. The first is the memoization table. This table stores results for every combination of index and current_sum. Since the number of such combinations matches the number of subproblems, the space required for the memoization table is proportional to n*s. The second component is the recursive call stack. The depth of recursion equals the length of the input array, n, so the recursion stack contributes an additional n space. When we combine these 2 components, the overall space complexity is dominated by the memoization table, which is n*s, with the recursion stack adding a smaller n overhead. Thus, the total space complexity is n*s. To put this into perspective, let's compare the optimized approach to a naive solution. In the naive approach, we would explore all possible combinations of plus and dash for the n elements in nums. This results in 2n combinations, giving the naive approach a time complexity of 2 to the power of n. The space complexity in this case would be n, due to the recursion stack depth. By contrast, the optimized approach leverages memoization to avoid redundant calculations, reducing the time complexity to n*s. Although the memoization table requires more space, the trade-off is justified given the significant improvement in time complexity. Additionally, since the algorithm systematically explores all valid subproblems, the time and space complexities remain consistent in the best, average, and worst cases, as they depend solely on n and s, which are determined by the input size and values. Finally, let's solidify our understanding with a mathematical proof of the time and space complexity. The total number of states in the memoization table is determined by the product of n, the length of the array, and 2*s plus 1, the range of current_sum. This simplifies to n*s. Since each state requires a constant amount of work, or O1, the total time complexity becomes n*s. For the space complexity, the memoization table, which stores results for all these states, dominates at n*s. While the recursion stack adds an additional n, it does not affect the asymptotic space complexity. Therefore, both the time and space complexities of the algorithm are O and *s. When tackling the target sum problem, there are a few common mistakes that can trip you up. First, failing to define an appropriate base case in recursion is a frequent issue. For instance, in problems like finding all subsets, neglecting to stop the recursion when you've processed the entire array leads to unnecessary computations and can even cause infinite recursion. The solution here is to ensure the base case is clearly defined to terminate recursion when the problem is reduced to its simplest state. Another mistake to watch out for is not accounting for negative numbers. Since this problem involves sums and differences, ignoring how negative numbers affect calculations can lead to incorrect results. To fix this, make sure you handle all possible values, positive, negative, and 0, and test your solution thoroughly. Lastly, overlapping subproblems in a recursive approach can result in exponential complexity if you're not careful. Many recursive solutions revisit the same states repeatedly. The fix here is to use memoization or dynamic programming to store already computed results, significantly reducing redundant calculations and speeding up your solution. Now, let's discuss a couple more common pitfalls. Misunderstanding constraints is another area where errors often occur. For example, if you overlook constraints like the array size, value ranges, or time limits, you might design an inefficient solution that fails to handle edge cases. The key here is to carefully read the problem constraints and tailor your algorithm to operate within those limits. For instance, you may need to optimize for O, n log n, instead of an impractical O, 2 to the power of n, complexity. Another potential oversight is not properly initializing variables. This mistake can cause bugs, particularly in iterative or recursive solutions, where variables might retain incorrect values from previous iterations. To avoid this, always double-check that variables are initialized and reset appropriately during each function call or loop iteration. These small adjustments can make a big difference in ensuring your code runs correctly and efficiently. Beyond avoiding common mistakes, there are strategies that can set you apart during interviews. Recognizing patterns is an essential skill. Many problems, including target sum, share common approaches like backtracking, dynamic programming, or greedy algorithms. Being able to quickly identify these patterns allows you to zero in on the right solution faster. Additionally, discussing trade-offs between approaches, like brute force versus an optimized solution, demonstrates depth in your problem-solving abilities. It's also important to ask clarifying questions about input constraints, edge cases, and expected outputs. This ensures you fully understand the problem and don't make incorrect assumptions. Finally, testing your code thoroughly is a must. Manually running through examples, especially edge cases, helps you validate your solution and catch errors early. Some related problems that can strengthen your understanding include LeetCode 78, Subsets, which builds foundational knowledge for recursive exploration, and LeetCode 416, Partition equals subset sum, which focuses on dynamic programming for subset sums. Other problems like combination sum on LeetCode 39 deal with generating all combinations that meet specific conditions, which is another great area to practice. Finally, let's explore some alternative approaches to solving the target sum problem. A brute force recursive solution is the most straightforward to implement but comes with significant trade-offs. While it's simple and intuitive, its exponential time complexity, O, 2 to the power of n, makes it impractical for larger inputs. Dynamic programming, on the other hand, is much more efficient for problems with overlapping subproblems and optimal substructure. It avoids redundant calculations by storing intermediate results, but it does require extra memory for the DP table and can be harder to grasp initially. Backtracking offers another option, where you prune invalid branches to reduce unnecessary computation. Although it's still exponential in the worst cases, it's typically faster than brute force. Finally, iterative solutions are worth considering. They often use less space compared to recursion, making them more memory efficient, but they can sometimes be less intuitive to design. Each approach has its strengths and weaknesses, and the best choice depends on the constraints and requirements of the specific problem you're solving. That brings us to the end of this session on target sum. We discussed brute force and dynamic programming approaches, highlighting the importance of optimization. Remember, dynamic programming is a key skill for tackling problems with overlapping subproblems. Thanks for watching, and be sure to like and subscribe for more content. Keep coding, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!